Okay. Okay, so last week we talked about water being a polar molecule. And remember, that's because the opposite ends have opposite charges. What charge does the oxygen atom have?
Negative.
Negative, and therefore the hydrogen has a positive. Can somebody tell me, remind us why that is? What does it mean? Why does it have a positive and a negative end, water? What's going on to cause it to have a positive and negative end?
The electronegativity of the oxygen molecule is greater than the oxygen. So the oxygen atom has a greater negative charge than the hydrogen.
Okay, absolutely. It draws the electrons closer to itself, and the electrons have a negative end. And so remember that that allows water molecules to form hydrogen bonds with each other. And hydrogen bonds is between the positive hydrogen and the negative oxygen of two different water molecules. So this shows you a picture for this one in the middle here. It's showing you that water can make up to 4 hydrogen bonds with other water molecules. So each hydrogen atom can hydrogen bond with one other water molecule, so the negative end here. And each oxygen can make up to 2 hydrogen bonds with 2 other water molecules, so a maximum of 4. With that. So because of water, and so those properties, water being polar and being able to make hydrogen bonds, gives it all of its other properties that make it unique. And so all the other properties go back and stem back to that polarity and making hydrogen bonds. So the 4 properties we're going to look at is cohesive behavior, that's another way to say cohesion, ability to moderate temperature, expansion upon freezing, and its versatility as a solvent. So we're just going to go through these here today, starting with cohesion. So collectively, hydrogen bonds hold water molecules together, and that's cohesion. Cohesion is an attraction between like molecules. So water molecule to water molecule, it's between like molecules. So you might want to, in parentheses behind there, put an attraction between like molecules, like 2 water molecules. Again, water molecules being able to do that stems back to being polar and forming hydrogen bonds. And so an example of this being helpful for living things is the transport of water against gravity in plants. Imagine you have a 50-foot tree and the water has to get to all the cells of that tree. Well, of that 50-foot tree, where does the water enter the plant? Through the roots, right? So the roots are on the ground, the water enters into the roots, but even the leaves, the cells of the leaves at the top of this 50-foot tree need water. So that water has to go all the way from the roots all the way to the top of the 50-foot tree, kind of defying gravity, because gravity has a force pulling it back down. So how does cohesion help with that? So when water, I'm going to pretend like I'm a tree, okay, so play along with me. Right? On the trunk, this is the trunk, branches, and my hands are the leaves, okay? So water goes in through the roots and goes up the tree here. So when you have water molecules together, they form these hydrogen bonds, right? And so what happens is you have a tunnel system all the way up, or the tree does. Let me show you this picture here. A tunnel system all the way up the tree. So here's the trunk of the tree. And if we were to cut this open and look microscopically, what you have, these little holes here, is the tunnel system I'm talking about as it goes through the tree trunk. And it goes, this is only a small section of it, it goes all the way from the bottom of the plant all the way to the top, and through the branches, and even through the veins of the leaves. The veins of the leaves transport water as well. And it's really a bunch of cells. So when we look at this cross section here, this right here is actually one cell right here. This is another cell right here, and they connect, and you can't see, but there are microscopic little pores that connect to them that water can move through. So you've got this kind of a bunch of cells that collectively make this tube system from the roots to the top of the tree. Those cells collectively are called the xylem. guys ever heard of that word? It's the xylem that moves water up it's a tunnel system that water moves up the tree. So what happens is, from the roots, if we look at, if I were to enlarge this, and so, and enlarge this here, so here's one of the cells, and here's the other cell, and so on, is you have these water molecules in a chain, kind of like a train of water molecules that are hydrogen bonded to one another. So you've got this whole train all the way from the roots, all the way up through the xylem, through the branches, through the veins of the leaves, and then to the cells of the leaf. So you've got this chain of water molecules in there. So that's the cohesion part. So how does that help to defy gravity? So what happens is on the top of the tree, you have your leaves, and at the bottom of your leaves, I don't know if any of you know this, but on the bottom of the leaves, you have little openings that open and close called stomata. Anybody ever heard of stomata? So they open and close. When they're open, guess what can happen? Some of those water molecules can evaporate, which means that they enter into the atmosphere. So those water molecules that evaporate, guess what? They were attracted to and hydrogen bonded to other water molecules, which were hydrogen bonded to others, and so on and so forth. So when those water molecules evaporate from your leaves of your plants, that's a good thing to some extent, because when they evaporate, they pull the chain of water molecules up. And so some of those water molecules that are all connected in this chain, some of those water molecules are used by the leaves of the plant to do photosynthesis, to make food for the plant, and so on. And so that evaporation of some of those, that loss of some of those water molecules are important. And so if you didn't have those water molecules that are stuck together in this train, you wouldn't draw and get the water all the way up to this top of the 50-foot tree. And so, that's how cohesion helps to transport water against the gravity of plants. Another thing that's going on in that same example is adhesion of water to the plant cell walls also help with countering gravity. And so, so as I drew up here, the water molecules are stuck together in the cohesion part, but the water molecules also adhere or are attracted to the plant cell walls. So they're attracted to the plant cell walls as well as each other, and so the attraction of the plant cell walls helps them so that they can defy gravity a little bit more as well, to kind of combat the force of gravity. And so adhesion is opposite of cohesion. We wrote that cohesion is attraction between like molecules. Adhesion is attraction between different types of molecules, like water and something else, all right? Like the plant cell wall, okay? And so, so both of those things are phenomenon occurring in plants. Going with cohesion, water on bodies of water can form what's called surface tension. It's the measure of how hard it is to break the surface of a liquid. And so water has a high surface tension because of the hydrogen bonds. And so it's related to cohesion, because the water molecules are hydrogen bonded to one another. And this is why this water strider can actually, how the water strider can actually float or walk on the water. So if we look at the surface of this water here, the surface, if the board was the actual surface, you have water molecules all hydrogen bonded together like this, forming these hydrogen bonds. And so what happens is these hydrogen bonds, when the water strider sits on the surface here, it spreads its weight out evenly enough where it actually doesn't break these bonds, so that water strider is able to stay on the top of the water without breaking those hydrogen bonds, and so it is able to walk on the water that way. And so if you put too much pressure in one area, that force is too great and it'll break those hydrogen bonds and you won't be able to walk on the water. So that's why we're not able to walk on the water, all right? But water striders are. And so, so that's called surface tension, again relating back to the water being polar and forming those hydrogen bonds. All right, so that's cohesion. cohesion, a little bit of adhesion. Next major concept with what water can do due to the polarity and hydrogen bonding is moderation of temperature. So water absorbs heat from warmer air and releases stored heat to cooler air. So it can absorb and release large amounts of heat with only a slight change in its own temperature. This is really, really important to living things. Now, we'd say when we talk about this, we use the words heat and temperature. I'm just going to do a quick little review of that. Remember that from other science classes, kinetic energy is the energy of motion. Water has motion. Every molecule, the atom within the molecule has motion. So the water molecules have kinetic energy. So when they're actually hydrogen bonded together, if you have a glass of water, all those water molecules are hydrogen bonded together, but they also have a kinetic energy. So those hydrogen bonds can be broken and reformed, all right, all the time. So the more kinetic energy the molecules have, the less stable those hydrogen bonds are. They break more often. All right, they can form, but then they break more often. And so what happens is that what increases kinetic energy? If you had water molecules and wanted to increase the kinetic energy, what would you do? That's something that you could do to increase the kinetic energy. Yeah, heat them. So you throw the beaker of water on a Bunsen burner, those molecules begin to move faster. And so therefore there's more heat in there. And eventually, the faster that they move, the higher the temperature gets, eventually some of those water molecules are going to do what? Evaporate. They move so fast that they actually escape, and they're in the air now, and they're far away, and they're not a liquid anymore. It becomes a gas. So kinetic energy is the energy of motion. Heat is a measure of the total amount of kinetic energy due to that motion. And temperature is how we measure that. So temperature measures the intensity of heat due to the average kinetic energy. So the molecules in that beaker of water or whatever that you're. And so, so water though resists temperature changes because it has what's called a high specific heat. So definition of specific heat. The amount of heat that must be absorbed or lost for 1 gram, so you're looking at volume, 1 gram of that substance to change its temperature by 1 degree Celsius. So if you took 1 gram of water, which is actually, for water is 1 cubic centimeter or 1 milliliter of water. If you took 1 gram of water, it actually, compared to other substances, you have to heat it up quite a bit to raise it 1 degree Celsius. That's why we say it has a high specific heat compared to other things. And so it resists changes in water and temperature, and that's because of those hydrogen bonds. They are hydrogen bonded to one another, which is a force that's holding them together. So as you increase the heat, it does start to increase the kinetic energy, but it resists that because of the hydrogen bonds holding them together. So it has a high specific heat because of the hydrogen bonding. So why is this important for living things? It minimizes temperature fluctuations to within levels that are conducive for life. So within limits that permit life. So, so let's think about this. We can think about this in a couple different ways about why it's important to living things. At the beginning of this with the overview, we said that cells are usually surrounded by a water-based solution and actually are made between 70 and 95% water inside your cells. So every single cell has a bunch of water inside of it and a bunch of water on the outside of it. And water resists temperature changes. So we are as an organism made out of trillions of cells, we are a water-based organism. We have a lot of water in us, and water resists temperature changes, which then helps our bodies to maintain a constant temperature and not get too high or too cold. So it's within the appropriate temperature range that is conducive to keep us alive, all right? And so another way that that's important is in bodies of water. So we're talking about lakes and ponds and so on. That, you know, a lake is getting inundated all day long, especially in the hot summer where the sun is more intense with the ultraviolet rays from the sun. And so it doesn't ever get, the water doesn't ever get to boiling. That would be way horrible for the organisms that live in there. And that's because of the resisting of temperature changes and so on, so the high specific heat. Another phenomenon is this, what's called the heat of vaporization, or this thing called evaporative cooling. So, we just talked about water evaporating as it absorbs heat energy and the motion of the water. It's higher. So, the transformation from liquid to gas, and that happens, as I said, as it absorbs heat. The heat of vaporization, definition, again, 1 gram. The heat a liquid must absorb for 1 gram, so in this case of water, 1 gram of water to be converted to a gas. And so, so what happens is, as liquid evaporates then, as it increases in kinetic energy and eventually has enough energy to evaporate, it's no longer hydrogen bonded to the water molecules as a liquid and goes off into the air, it cools the surface that it is evaporating from. So its remaining surface cools off. So whatever surface water is evaporating from, it cools it off, whether or not that be a table, right? If you spill some water and just spread it around and it evaporates off of it, it'll cool off the table in which it's on. How this relates to living things, like for us, is what?
Sweat.
Yeah, absolutely, sweat. We sweat when our body temperature does what? Goes up, right? All right, so your body temperature is going up. So one way to resist temperature fluctuations, we said, were mainly water. So water resists temperature fluctuations, but then we also sweat and put water on our surface of our body. So we're hot, our body, as a natural defense, we start to sweat. What happens, the sweat, is as it absorbs heat, all right, it begins moving. The kinetic energy, the higher kinetic energy, eventually evaporates. So those molecules that are moving the fastest, all right, and have the most heat evaporate off, cooling off the surface in which you are, it's evaporating from, which in this case is your skin. It cools off your skin. And so therefore, often, like last week was really, really hot. And so when you sweat, if you want it to feel cooler faster, what kinds of things do people do? So you're hot and you're sweating, what kinds of things would you do to cool yourself off?
Drink water.
Okay, drink water. So drinking water, especially cold water, gets that temperature, your internal body temperature. You drink ice water inside to cool down. That is one way to cool it down. So you're cooling down the organs and so on in your core. But the sweat.
You go swimming.
Okay, you go swimming, exactly the same thing, that you're cooling down your body temperature by immersing yourself into a cooler body of water.
You use a fan.
You use a fan. Now this relates directly to the sweating thing with the evaporative cooling. If you go in front of a fan, you feel cooler a lot faster than if you're not in front of the fan, right? Can somebody explain why that is? As it relates to the properties of water that we're talking about.
As the air moves over you, it's taking heat away, along with the water vapor from your sweat.
That's right. It's actually increasing the rate of evaporation of that water from you. And so, therefore, taking heat away and making you feel cooler. So, in front of a fan increases that rate of evaporation, which cools you off at a lot faster, which is also you feel drier too eventually because it's all of that's evaporating off of you. And that's also why on really hot, humid days, like it was last week, when when a day is really humid, there's a lot of water in the air, and so the air itself is almost saturated as the humidity goes up. And so your body, you're still hot, so you will still sweat on a humid day. Your body's trying to cool yourself off. But what happens on the humid day, if the air is already saturated with water, it reduces the ability for the water to evaporate. So your body's still sweating. The water stays on your skin, but the air is so saturated that the water won't evaporate from you, so you feel even more miserable, all right, on humid days, so that's why, okay? So, is the reducing the evaporation. So evaporative cooling then helps stabilizes temperatures in organisms, like we just talked about with sweating, but also bodies of water, those in lakes and so on, the water molecules that evaporate and take heat away, so the body of water stays fairly cool and never, like I said, gets to a boiling point or anything like that, all right, which is a good thing for the organisms. One other thing with it and how it relates to, in this case, organisms in a standing body of water is floating ice. So ice is, water is a solid. Ice floats in liquid water. Why? Because the hydrogen bonds in ice are more what we call ordered. They form a crystalline structure, making ice less dense. There's more space between the water molecules than there is in liquid water. And I'll show you a picture here. And this is important for living things. If ice sank, all bodies of water would eventually freeze solid, making life on Earth impossible, because in the first winter if it froze solid, everything would die, all the organisms in the body of water. So what happens is why ice is important is that as it floats, it forms a layer of insulation. So it freezes only down to a certain point, never freezes down to the bottom. It freezes to a certain point, and what happens is then it acts as an insulation barrier between the frigid, cold air and the water below it. So all the organisms below can survive the winter time and not die. All right, so it's very, very important for living organisms. And this picture here shows you about why ice floats. So it has a little picture here. This is the bottom of the ice, and this is supposed to be water. Here's your little living organism in the water. We're looking at ice over here and water over here. The circles are supposed to be the same size, showing you that you're looking at the same volume of water. And you can see that in ice, there are less water molecules in this space than there are with liquid water. That's what makes it less dense. Density, mass over volume, so it's like kind of the number of water molecules, let's say, per given volume, which is the circle, is less than over here. So why is it less? If you look here, these water molecules, they're still forming hydrogen bonds, just like the liquid water molecules, but what they do is they structure themselves into this crystalline structure, making there more space between the water molecules, which then means that in that given volume, in that given space, there's less water molecules. And so the ice will float on top of the water, so which is helpful for living things. So that's why that is. All right, and then the next major kind of category of properties of water is that it's a great solvent. Sometimes it's called the universal solvent. And so let's talk about what a solvent is as it relates to a solution. So a solution, by definition, is a liquid that's homogeneous in its mixture of substances. So what does that mean? It's equally mixed. So two words that go with making a solution is the solvent and the solute. And so if I were making, let's say, Kool-Aid, so I have like the powdered flavored sugar and water. Which one is my solvent? The water. The solvent is what's doing the dissolving, it's the dissolving agent, and whatever's going to dissolve is your solute. So a solvent is the dissolving agent, and a solute is the substance that then is dissolved. And water is very versatile in its ability to dissolve substances due to its polarity. So due to its polarity, it's positive and negative charges. So what we're going to basically see is water is really good at dissolving substances that have some kind of charge, because water will be attracted to its charge because water has a positive and negative end. So, and we call any solution that the solvent is water, we call it an aqueous solution. Aqueous refers to water, water-based. So let's look at those types of things that water can dissolve. It's an effective solvent because it readily forms hydrogen bonds, and it does that with molecules that have charges on them. So for instance, an ionic compound, when an ionic compound is dissolved in water, each ion is surrounded by a sphere of water molecules. And they call that sphere that surrounds the ions a hydration shell. So remember, an ionic compound is between two ions. Remember the transfer of electrons? So this picture here shows you it was sodium chloride, which I also used last week in the review pictures with chemistry. So what you have here is a beaker of water. This is supposed to be a salt crystal. So this is salt right here. Just table salt, so NaCl, and it's ionic compound because the two ions, sodium is positive, the chloride ion is negative, and that's your crystal of salt. So what it's doing is showing you here the crystal, and this part right here is supposed to be your salt crystal. So notice here the salt crystal is made out of many sodium chloride compounds put together to be able to see it, because you can't see just one. So you have many of them, sodium chloride, and so on and so forth. So that's your crystal. So what happens is when your water meets the crystal, the ends of the water are attracted to the various ions. So you can see that this sodium and this chloride ion has already been broken away from the crystal. So what happened is, this, let's say, started out as being part of the crystal. So the chloride ion is negative. So what would happen is the water molecules, all the hydrogen parts of the water molecules would be attracted to this negative chloride ion. And as it all those water molecules bind to it, it kind of pulls, and eventually that chloride ion will break away from the crystal, and the water molecules will surround it. So that's what we see here with all these water molecules with the positive ends, the hydrogens, surrounding that chloride ion, and that's called a hydration shell around it. So it has surrounded that chloride ion. The opposite has happened with this sodium ion. They had a positive charge, so the water molecules on the surface of this crystal, all the negative oxygens, surround it and going to break that ion away, and when it happens, the water molecules surround it like this and form a hydration shell. And so what happens when you have a large crystal like this in water is the water molecules will work on the surface area, the surface exposed to the water, breaking off the ions one by one. And we'd say that these are dissolved in the water, all right? They're dissolved in the water, that's what happens here. And so it'll continue, these other water molecules that are in this beaker will continue working on the surface area all around this crystal until eventually every single sodium and every single chloride ion is surrounded by water. And then you have them all separated, no sodium and chlorides are binding with one another, and we would say that it's dissolved in the water, all right? So that's what happens with an ionic compound in water. So you can see that if there was no charges here, would water want anything to do with this crystal? No, if there were no charges whatsoever, water wouldn't be attracted, and therefore it would just sit on the bottom, all right? Nothing would happen to it, all right? Unless somebody physically broke it up or something like that, all right? So it has to have some kind of charge. So that's an ionic compound dissolving in water and making a salt solution in that particular case. Water doesn't only dissolve ionic compounds, it also dissolves compounds made up of non-ionic polar molecules. Sometimes we just call them polar molecules. These guys, molecules that are polar, whenever we say polar molecules like water, remember they have polar covalent bonds. Have polar covalent bonds. Somebody remind me from last week what that means. Let's just start with covalent bond. Covalent bond means that the atoms of that molecule are doing what? Sharing electrons. When I throw polar in front of it, what's going on with those sharing of electrons? It's uneven, all right? So it's an unequal sharing. So when you have a molecule that it has, the atoms in that molecule are held together by polar covalent bonds, what's true about some of the atoms in that molecule? Water has polar covalent bonds. This is a polar covalent bond. What's true?
So the atoms are partially positive.
That's correct. Some of them are going to be partially positive hydrogens. Some of them are going to be partially negative. And so when you have polar covalent bonds with that, you might want to write then that there's partial charges on the atoms. All right, so you have some charges. Remember I said that water usually dissolves substances that have some kind of charge on it. And so if you have a polar molecule that has a charge, water can dissolve it. So even large polar molecules such as proteins can dissolve in water if they have either ionic and polar regions. Why? Because if they have regions that are formed by ionic bonds, there's charges, and if they're polar regions, there's charges as well. So that's why they have, I'm going to put here, they have charges. That's why on the ionic and polar regions. That's why it can. So, a protein. I'm going to show you a couple of pictures in just a second of a protein, but just remember from bio what proteins are made up of. They're long chains of smaller molecules. How do you remember? Long chains of smaller molecules. And it starts with an A. Let's see if you're... Amino acids. All right, they're long chains of amino acids. And so what happens is, so AA is amino acids, so it's a long chain of amino acids, and that's the most basic way to think of a protein. But really, it's not just a long chain of amino acids. What happens, like, so if this is like a ribbon representing a long chain of amino acids, it's not really in that shape usually. Proteins, the chain of amino acids usually fold on one another and so on, and so you end up getting this three-dimensional shape that looks like kind of a glob like this, due to the chain of amino acids folding on itself and so on. And so that's going to be helpful for when we look at the next picture. So what happens here is that you have atoms here that can be bonded ionically and have charges, or have polar covalent bonds. So you can have atoms that are in here that have positive charges and negative charges and so on and so forth, due to the way that the atoms that make this up bond to one another. So you can have this molecule that has charges on part of the molecule but not others, and so on. So that's what this picture is showing you here. It says down here it says it's a lysozyme. This is, I'm going to put in parentheses, it's just a type of protein. Now your book often shows proteins like this one big blob here, and really what they are is this chain of amino acids that are folded up and so on. And what you can look at here is each one of these little kind of bubbles inside of here is like an atom. So this atom is bound to this atom and so on and so forth. And it's just giving you the overall shape, but it's really a molecule with all these atoms bonded together. So what happens is when you put a protein that has polar regions that have charges on them, so if you have parts that have, let's say this, let's say this atom and this atom form a polar covalent bond. So let's say this one right here, this atom is more electronegative, so it's going to draw the electrons towards itself. So this atom would be negative, have a partial negative charge. This one would have a partial positive charge. And so what you have is you can have all these different atoms of this larger molecule, and if they have polar covalent bonds, you can have the charges within those atoms. And so that's what this is showing you here. This is showing you that same protein molecule, and you stick it into water. And that protein molecule, if it has charges, the water molecules are going to be attracted according to the charges. And so when you look at this part here, they're enlarging that particular part of the picture. So we're just looking at this part of the lysozyme protein molecule. And so that protein at that particular point has a partial negative charge and a partial positive charge. So you can see here the water molecules at that point are being attracted, positive hydrogen to the negative and negative oxygen to the positive part there. And you can imagine if that's going on all over the place, where if there's charges on this larger molecule, the water molecules are kind of surrounding it appropriately. And so then what happens is, going back to this picture, is if those water molecules are all binding together, what it can do is interfere with the three-dimensional shape, and the protein can kind of unravel, and then we'd say it dissolves, all right, in the water. Okay, so that's how covalently bonded things can actually dissolve in the water. So that's how sugar also. Protein is an example of that. Sugars are an example of that, where they can dissolve in water. All right, so long story short, is anything with a charge water can work to dissolve it. And so, so we call substances that water is attracted to and therefore can't dissolve, we call those, what do you think, hydrophilic or hydrophobic? Hydrophilic. Do you guys remember these words from biology?
Yes.
All right, so a hydrophilic substance is one that has an affinity for water or attraction, and that's usually because it has a charge of some sort on it. And therefore, a hydrophobic substance is something that does not have an affinity for water, and the reason because of that, is that there are no charges. So what kind of bonds can make up atoms of something that is hydrophobic? So hydrophobic, think about, is it going to have a charge or not? No charge, all right? Otherwise, water is going to be attracted to it if it has a charge. It's going to have no charge. So what kind of bonds did we talk about that can be formed between atoms of a molecule that would result in no charge? An example we used in our review pictures was O2. O2, if I draw that out, how they're bonded together, is like this. They form a double bond between the oxygen atoms. There's no charge on O2. What's true about those lines that I just drew, the bonds between those?
Is it a non-polar covalent bond?
It is a non-polar covalent bond. And what does that mean? Non-polar covalent bond. So the electrons are, they're shared the same. They're shared equally between the two atoms. And in this case here, this is a pretty easy example because the oxygens, they're the same type of atom, so they will have the same electronegativity and therefore will draw electrons equally. And so there's no charge on either one of those because the electrons are shared equally. And so that's what we, for hydrophobic substances, we will see non-polar bonds in those. What's an example? A hydrophilic substance, you know, I just used two examples with dissolving, so like the salt example and that protein example. What's an example of a hydrophobic substance?
Maybe oil?
Oil, all right. Oil, the bonds between the molecules in oil are hydrophobic, covalent, non-polar covalent, so that makes them hydrophobic. So what happens is when you put a hydrophobic substance into water, the water molecules are not attracted at all, let's say, to the oil. So what happens is even if you shake it up and the oil gets mixed with the water, they'll get mixed for a while, but they will separate out. And the reason why is the water molecules are more attracted to each other. They're not attracted at all to the oil. So just this, the water molecules bond to one another, they exclude the oil, and the oil will separate out because of that, and because of the water molecules hydrobonding to each other. All right, so as we look at this water-based solutions, solutes, remember something, it says solute concentration of aqueous solutions. So solutes are something dissolved in water. So we're going to relate this to in living things like a cell or in an organism. So most biochemical reactions, chemical reactions that occur in living things, occur in water. And so inside of our cells, that would be like the cytoplasm. And chemical reactions depend on the collision of molecules, and therefore on the concentration of solutes in an aqueous solution. So what does that mean? So let's pretend that our room is a cell. So the air is like the cytoplasm. And so for reactions to occur, molecules they're not little organisms, they're not alive, they don't have eyes. So in order for a reaction to occur, the reactants, I'm just going to use generic molecule A and generic molecule B. The reactants have to come together and then they can react and turn into product. That, they don't find each other and beeline it for each other and say we need to react. So what's happening is inside of your cells, you have molecule A, molecule B, they have a certain kinetic energy. They're bouncing around inside the cell. And so for a reaction to occur, they have to actually collide with one another. So if you have a very low concentration of these reactants, let's say we only had one of each. So let's say molecule B was in that corner and molecule A was in that corner. If you have very low concentrations, the likelihood that those two molecules are going to be randomly moving and randomly bump into each other and for that reaction to occur goes down dramatically if there's low concentrations. But if you add a bunch of those molecules into the room, a bunch of A's and a bunch of B's, then as they randomly move around, since there's so many of them at a high concentration, they have a greater chance of colliding and therefore that reaction occurring. And so that's what that means here. So concentration of molecules, we're going to be looking at this over the next few chapters. We're going to be doing some labs with it and so on. It's very, very important in determining whether or not reactions occur at an appropriate rate or not. All right, and so having those concentrations are a big deal. Okay, so one way to think about concentration is with what we call molarity. So molecular mass, just remember this, molecular mass, the sum of all masses of all the atoms in a molecule. So you take the individual masses and add them together to get the whole molecule's mass. And the number of molecules are usually measured in moles. So remember this, moles sound familiar from chemistry? Moles is a quantity of substances. 1 mole is 6.02 times 10 to the 23rd molecules. 1 mole of something. And so we measure concentration here in biology. We're going to use a lot with molarity. And so molarity by definition is the number of moles of solute per liter of solution. So how many moles per liter of solution? So for example, what we call a molarity is represented by the capital letter M. So a 1 molar solution, when we say a 1 molar, or we can say 1 molar, like that, solution of let's say, of sugar, let's say. How we make that is we put in, it's 1 mole of that sugar and 1 liter of water. And that's concentration. How many of something, because a mole is like actual number, 6.02 times 10 to the 23rd molecules of sugar in that liter of water, and that is your concentration. So a 1 molar solution is more concentrated than if I had a 0.5 molar solution. A 0.5 molar solution, a 0.5 compared to 1 is half, right? So what would we have here in a 0.5 molar solution? We'd have 0.5 moles, all right, or half of a mole, all right, for that liter of solution. And so it's a measurement of concentration, all right? And so the higher molarity, the higher the concentration, lower molarity, the lower the concentration of that substance in the water. Remember, the higher concentration in living things, the more reactions occur. So let's go over an example of calculating molarity. So we're going to use just simple table sugar. So find the molecular mass of sucrose. And you guys, I'm going to go over masses here. I'm going to copy. I had forgotten that you need a periodic table because ironically there's so much chemistry and biology, but our biology publisher did not put a periodic table in our textbook, so there's no periodic table. So I'll make some copies for you, but you have the sucrose, C12H22O11, so it has 12 carbon atoms, 22 hydrogen atoms, 11 oxygen atoms. In order to find the molecular mass, the mass of the whole molecule, we need to find and know the individual masses of carbon, hydrogen, and oxygen. So to do that, anybody remember the mass of carbon? 12.011. That's right. And for this class, we'll just round it off and say 12.
Because we did that so many times.
Right. Carbon is 12. What's hydrogen?
That was 80.
1.008.
Yeah, and I'm just going to put 1 for this class. This is good enough. And oxygen, anybody remember oxygen?
50.99994.
Nice. I'm going to round that to 16. Right. All right, so those are the individual masses for each of those individual atoms. What I'd like you to do right now is then calculate the molar mass. Or not the molar mass, the molecular mass.
Were we supposed to check in here?
Sure.
Shoot. I didn't hear the announcement. So
I know that was weird that they came, yeah, they came on. Okay, all right, I'll change your.
we're taking notes.
We are, and I'm recording them, so like you can, and I sent this morning a link to my YouTube channel, so if you want to, you can either watch it or get notes from somebody else. Okay. All right. You guys get 342? All right. 342. Dalton's is a measurement, but we're gonna run out of time, aren't we? We get out of here 7. All right. All right. 342. I'll stop here, and we'll pick this up after we finish the stations tomorrow. I think we only have a couple tomorrow to finish up. All right. So, and then we'll come back to this. All right, so I want to give you enough time to get your phones and. If you just use 342, you might want to much you can realize in the state, yeah.